All right. As promised, we're going to have a quiz this morning, but we want to review real quickly. I need to find out about next week too. I heard, with the modified week for next week, with everything that's going on, I'm not sure how often we're going to be able to get together. I don't know that we're going to be able to test before then, which means it's revival week and all that stuff. So it's going to be very different. I haven't heard exactly what our schedule is going to be like in first period. So it may be that we're not able to test this material because it would be this week, right? I don't think we're going to test this material this week, but that also means then we're going to have a weird week between now and testing, which isn't going to be classes every day. So you're going to have to retain some of the stuff through a little bit more adversity than maybe you've had in the past. All right? So real quick review from last week, the end of last week. The last two sections we talked about were reactions between acids and bases, and actually acids and bases in two different categories. We had acids, an acid and a base. This is just a general formula, reacts to produce a salt and water. And we had another situation where we said an acid and a base react to produce ions. Two different cases. Where was the qualifier in each one of these? Where did we, in the base, okay? And how do we differentiate between these two bases? Okay, so in this case, the top one, this is an ionic base. This one is a covalent base. And the ionic base is predominantly going to include what ion? In most cases, you're going to see an ion recur over and over and over again in ionic bases. Correct, the hydroxide ion. So if you look and you see an ionic base, and if it has a hydroxide ion in it, or if you see OH together, not every time, but most times that's going to be the polyatomic ion that's going to bond to a metal, right? So the ionic base is going to be a metal and either a nonmetal or, in this case, a polyatomic ion that's going to react with the acid to produce water and a salt. Now, the acid is going to give up a hydrogen. Remember the different ways you can identify the acid? Either you know that, hey, this is hydrochloric acid, therefore it's acid, because you've memorized the formula and the common name, or it starts with a hydrogen. In most cases, it starts with a leading hydrogen in its symbology. So looking over to the base, and it's going to be a metal and combined ionically with something else. It's going to produce a salt. And that salt, hello, that salt is going to come from the combination of the non-hydrogen portion of the acid and the non-hydroxide portion. You're going to get the metal from here and then the other portion from here to produce this salt. Remembering that salt is not always NaCl. It could be KCl. It could be basically any ionic bonded metal, nonmetal. Okay, so you're going to produce a salt and water. Down here, this was the second case with covalent bases. The difference here being that just like up here, the acids are going to donate hydrogen ions, protons, right? Both of these could be polyprotic, meaning they could be more than one hydrogen. Could be diprotic for 2 or triprotic for 3. But they're going to donate hydrogens to, in this case, this covalent base. Now, in this acid-base reaction, because it's ionic, the base actually breaks apart and forms new molecules. However, in a covalent base, what does a covalent base do? Does it break apart? No. The covalent base stays together. But it does morph. It does change in some way. And remember, what the covalent base will do is it will accept one hydrogen from the acid. So when you end up with your ions over here, what you're going to see is your covalent base plus an additional hydrogen appear on this side, as well as the non-hydrogen portion of your acid appearing as an ion on that side of the reaction. Okay? Did I help or confuse? I see at least some confusion, but is that a good refresher of what we're doing here? Okay. Hydrogen to part of the base to form water, the non-hydrogen portion and the metal portion combining to form the salt. In this case, acid base, a covalent base, will accept one hydrogen, only one. So that means if you've got a polyprotic acid, you've got something that has an H2 or H3, it's donating more than one hydrogen, you're going to have more than one base to accept that. So if it has two hydrogens it's donating, you're going to have at least two molecules of the base to accept the two hydrogens, or three molecules of base in order to accept a triprotic acid's hydrogens. Okay, so it's going to donate 1, 2, 3 hydrogens, whatever. You're going to need one molecule of base for every hydrogen that's donated. And the ions are going to be the base plus a hydrogen and the remainder of the acid. Okay? So, I'm going to go ahead and take out a blank piece. I'm going to ask a class representative to help us determine the quiz. Savannah? 1, 2, or 3? Just pick 1, 2, or 3. Number 2. Number 2 is should be a, yep, 2. Complete and balanced equation. Sydney, 1 or 2? Number 1, okay. Complete and balance. This is number 1. This is number 2. Okay. So obviously we've got one of each situation, right? What are we looking at here? This is, if you know the name, what is this? Hydrobromic acid. We also, not only is it hydrobromic acid, but of the two, it starts with a leading hydrogen, right? It's also a covalent molecule, okay? So not, in each case for this course, we're going to talk about covalent acids. So if you have a covalent and an ionic, the covalent one is going to be the acid, okay? And standard form is, if you've noticed, the book tends to always write the acid and then the base. So they pretty much give it to you every time. But you should see from all of those different indications that hydrobromic acid and sulfuric acid lead both, so the acids lead in both of these equations. They're followed by the bases. Now, question here is, which category are we looking at for each one of these? And it flows just like the board. Ionic, covalent, this is an ionic and a covalent. You know, if we did the NH3 molecule before, we figure out is it ionic or covalent, then do the geometries and all that. Okay, because we have two nonmetals, right? The nonmetals are going to form a covalent bond. They're going to share an electron. Up here we have a metal and a polyatomic ion. And so we're dealing with, can you get it? There we go. So you're dealing with acids and an ionic base and a covalent base. So without worrying about exactly what it is, we know that on this side we're going to end up with a salt and water. It's going to produce a salt and water. And what is the salt going to be? Well, if we look back here, the hydrogen is going to get donated to the hydroxides to produce water. We're not worrying about balancing it right now. We're just looking at the components, okay? We'll do the balance in a moment. And we also then know that the non-hydrogen portion of the acid is going to combine with the metal ion from the base to produce the salt. And remember, for the ionic salts, we write the metal, then the nonmetal portion. Well, the metal portion is coming from the base, so it's going to be some form of calcium and bromine. Okay, some form of that molecule. Now, looking at the bromine, what charge is the bromine ion going to have? It's a column 7 element. The hydrogen is a +1, so the bromine here would be a -1, right? The bromine is going to be a -1. What's calcium? If you remember from, it's a column 2 element, right? Or if you look over here and say, wait a minute, I've got hydroxide. Each hydroxide has a -1 charge. So in the balanced molecule, if I've got two 1 minuses, the hydroxide together are 2 minus. What must calcium be? 2 plus. A 2 plus and 2 1 minuses. So it's balanced. So calcium's a +2, bromine's a -1. So what's my chemical formula for calcium bromide? CaBr2, calcium bromide. Now let's go through and balance it. I have a hydrogen and 2 hydroxides, okay? How do they come together to form H2O? I've already got 2 hydroxides, so what must I need? For my 2 hydroxides, I need how many hydrogens? If I got 2 hydroxides, each one of them needs 1 more hydrogen, right, to be H2O? So I need to have 2. 2 hydrogens bond with 1 each of the hydroxides to form how many waters? 2. 2 hydrogens. The reason I have 2 is because I need to consume both of the hydroxides. I need 1 hydrogen for each of these 2, meaning I need 2 altogether, and 2 H's plus 2 OH's produce 2 H2O's. Now looking at the ion, I now have 2 bromines and 1 calcium, a 1 to 2, and I have a 1 to 2, so I'm good. So this is my balanced reaction for hydrobromic acid and calcium hydroxide. They react to produce calcium bromide and 2 water. Okay, any questions on that? All right, let's go to the second equation then. We have sulfuric acid and ammonia. Is ammonia a covalent or an ionic molecule? Again, it's 2 nonmetals. 2 nonmetals form a covalent bond between them. So we're looking at this case here, an acid and a covalent. Okay? It's going to produce ions. And how does it produce those ions? It's going to take the hydrogen from here and combine it with the complete base to produce NH4 plus. Okay? It's donating hydrogen ions, plus 1 hydrogen ions, to the base. And so all we're doing is taking the base and upping the number of hydrogens by 1 to be NH4. Its charge, it received a positive, so the molecule was neutral and it becomes 1 positive. Now, what's left over then? The non-hydrogen portion of the acid, which we rewrite on this side just as itself, SO4, 2 negative. How do I know it's 2 negative? Well, I could have memorized it, right? Because it's polyatomic, we're supposed to know. But also, if I forgot that, I look over here and say, wait, this is a neutral ion, or a neutral molecule, and it loses 2 positives. It must now be 2 negative. And so that's how we get the 2 negative charge. Now let's look at the balance real quick. For every I need 1 molecule of base for every hydrogen ion donated, right? Because this can only take 1. That's the rule. It can only take 1 hydrogen. How many hydrogens do I have to donate? 2. It's a diprotic acid. It's giving 2, so I need to have 2 to accept both of those 2, which means I then have 2 of the ion. And then looking back, all I'm doing is taking the remainder. How many do I have? I have 1 of them, the implied 1. So I just bring the 1 over, and so that's our balanced reaction equation for sulfuric acid and ammonia. Okay. Let me see how we did. Pass them on back to Aaron. That's it. All right. Remember, quizzes are meant to be blessings that help, not frustrations that hurt. I'm sorry if it doesn't work out that way for you, but we're moving on to a new concept called molarity. It has nothing to do with dentistry. Don't erase? Okay. I'll give it just a minute. Okay. You have to listen close to get my jokes because they're really bad and they're hopefully very quick, right? What did I just say about molarity? Has nothing to do with dentistry. That's right. Molarity has nothing to do with dentistry. It's also bad when I do stupid stuff like that in the middle of a class because I don't bother to edit it out. So this is going to go onto YouTube and people are going to go, what a dork. Okay. Okay to race now? Okay. Hopefully somebody got 100 so I don't have to recreate this as an answer key. But I think we can do it pretty quickly. Okay. We're going to take a step away from acids and bases proper and just talk about this idea of molarity. And hopefully you understand the idea of molarity, and then we'll start applying the idea of molarity. Molarity has to do with concentration. And in the book, 3rd edition, they give an example of a cleaning agent referred to, its brand name is the Works. And the Works is basically a diluted acid. It's 3% hydrochloric acid and it's 3 and 97, obviously. Let's go ahead and write it up there. 3 and 97% water. We'll get into that. It's actually based on the counts, the number of moles. Okay, so it's 3% hydrochloric acid and 97% water. Now this is sold as a commercial cleaning agent. You go to the store, you buy it, you spend a lot of money for a lot of packaging to get the Works, to go and clean, primarily bathrooms, porcelain, surfaces, things like that. And you know that it's water, which you can just get right out of the tap, and 3% hydrochloric acid. You can also go to the hardware store, like they say in here, and you can get what's called muriatic acid. Muriatic acid is a common name for a solution which is 30% hydrochloric acid and 70% water. Okay? Which do you think is more expensive? The Works. Because it's a brand that's packaged that you purchase in a supermarket, common distribution. This, you have to go to the hardware store and purchase it specifically. But with a little bit of chemistry, guess what you can do? You can make the Works by buying muriatic acid and diluting it. Now, why do they sell muriatic acid at 30%? Why don't they sell you like 90% hydrochloric acid? Yeah, you'd kill yourself. Hey, wait a minute, I thought I had 10 fingers. What happened? Yeah, some bad things could happen if you get much more concentrated with that. But muriatic acid is used by a lot of professionals for cleaning, okay? And they can make their own cleaning solutions. They just have to figure out what percentage of acid they're willing to actually work with. So we're going to get into this idea of molarity. Molarity is a way of understanding concentration. So in just a very basic understanding of concentration, like think of orange juice. You can go to the store and you can buy a gallon of orange juice. Or you can go to the store and buy this frozen little can, right? Take it home, put it in a pitcher, add 3 cans of water, whatever it is, and mix it up, and suddenly, what do you have? No, you have orange juice. You don't have Kool-Aid. Kool-Aid's very different from orange juice concentrate. Now, granted, they do some other things too. Some of them take the orange juice and they pasteurize it, and they do other things to it to purify it. Whether you believe that's better or worse for you, it's debatable. But basically, why do they make concentrated orange juice? Takes up less space. Okay, in taking up less space, that means in transportation, because just like with the works, okay, a lot of your cost is taken up with packaging and transportation of the product to the store so you can buy it. If you can take something and reduce its volume dramatically, you can reduce the packaging cost for it and you can reduce the transportation cost for it. If I take an 18-wheeler, tractor trailer full of liquid orange juice, or if I can take the same space and pack it full of orange juice concentrate, I can bring a lot more orange juice, if you will, to market in different places. I can load up a lot more potential orange juice in concentrate form. Concentrate, basically all they do is extract the water from it. And so when you get it, you add your own water back into it. If you were to take the orange juice concentrate and melt it, you'd have this really thick, syrupy, sticky, gooey kind of a thing. And you look at it and go, what is that? I'd say it's concentrated orange juice. It's the non-water part of the orange juice that you buy when you buy it in the jug form. The only difference is water is being put back into it. So then the question is, what's healthier? The original water that was in the orange juice that was brought up by osmosis and then capillary actions up through the roots and up to the fruit and then filled it like Florida water filtered by the plant, or in our case, Louisville water. Okay? But the difference is water. Where's the water sourced from? How did it get to be into the juice? But you can transport a lot more, therefore less cost per ounce of final orange juice if you do it by concentrate. So concentration is really about how much of the stuff you're talking about is in a particular volume of space. And in this case, we're going to talk about molarity. Later on, we're going to talk about molality, which is something different. So you're going to need to be able to differentiate between molarity and molality. One of them lacks the R and replaces it with an L. Molality and molarity. Now we're talking about molarity. Molarity with the R, molarity. In your book, they give the definition on 330 that molarity is a concentration unit. So we're talking about how much stuff is in each volume of space. A concentration unit that tells us how many moles of a substance are in a liter of solution. It is determined by dividing the number of moles of a substance by the number of liters of solution. So, abbreviated form, it's capital M is a symbol. Molarity is equal to the number of moles divided by the number of liters. The molarity is the number of moles divided by the number of liters. So let's say we have a jug of water, let's say. Jug of some kind of solvent, okay? And we're going to put a solute into that. We're going to put something into the liquid. Let's say we're making salt water. How's that? Something refreshing to drink after a hard workout, right? Let's go drink some salt water. I'm just trying to use something maybe you'll remember. So his big old swig of seawater, right? Yeah, nothing like it. Apparently you not have all had the opportunity to drink down a lot of seawater, but I have, okay? It's not all that great. Number of moles per number of liters. So let's say, for example, that we're making salt water, and we want to get to a certain concentration. You know, we have this salty water, and when we put maybe a teaspoon of salt into a gallon of water, and we stir it up and we drink it, and like if you know you're looking for salt, you might taste it, but it's not really that much. And so we go ahead and we add more salt to it. You take a sip, it's saltier, and as you add more and more salt, sodium chloride, to the liquid H2O, hopefully you can agree with me that you would expect that water would taste saltier and saltier and saltier. And as you're tasting that salt water, hopefully you recognize that as I'm drinking salt water, I'm tasting not only the sodium chloride, but I'm getting a sense of how concentrated it is. The more salt is in the solution, the more salt I taste, the saltier it is. It's not so much a matter of a different taste, it's about the intensity of the taste, right? I'm tasting a lot of salt. The assumption is there's a lot of solute, the salt, a lot of salt has been poured in. So the higher the concentration, the more of the stuff that I have in that given volume, okay? This is going to tie into this idea of molarity being used in stoichiometry. It's going to be important for us to understand that, because the more concentrated something is, the more of it we get for any given volume of that liquid, that combination, that solution, and it's going to directly relate into how many moles of that substance we have. We're going to branch into that in just a moment, but for right now, let's just consider this whole idea that molarity is the number of moles of something divided by the volume of the solution that it's in, both it and its solute, or excuse me, its solvent. Probably the best way to do that is just look at the example, see the math, and recognize that what we're talking about here again is concentration. How much of the stuff, the solute stuff, do we have in the given solution? Example 9.4 says, what is the concentration? What is the concentration? And it tells us in parentheses, in units of molarity. So molarity and concentration, think of those things as being synonymous. What is the concentration in units of molarity of sodium hydroxide if there are 2.6 moles of the substance in a solution with a volume of 534 milliliters? So the molarity is the number of moles divided by the number of liters. We're told here that we have 2.6 moles in 534 milliliters. 2.6 moles of NaOH, of sodium hydroxide, and that 2.6 moles is in 534 milliliters of solution. Milliliters of solution. Now, one thing to recognize, excuse me, one of the things to recognize here is that if, let's say I was in the lab and I was making this, I had a certain volume and a certain number of moles of sodium hydroxide already mixed together, and I decided I wanted to add some sodium hydroxide, right? I wanted to add more. If I poured more of the solute, more of the sodium hydroxide into the mixture, I would increase the concentration, yes, but I would also at the same time increase the volume of the solution, right? The volume would be affected by me adding more stuff to it. If I have a solution of sodium hydroxide in a solution already, and I add more sodium hydroxide, I'm increasing the number of moles, but I'm also, to a much smaller degree, also increasing the number of liters of my solution. Make sense? Think of it this way. I have a beaker with water in it. I've mixed in my sodium hydroxide and it's at a certain level. Do you accept that if I add more sodium hydroxide, the level would go up? That's all I'm saying. The level would go up. I would have much more sodium hydroxide and I would have a little more volume if I did that. And we'll deal more with that interplay between adding solute and increasing volume later on. What they're saying here now is, hey, you've already mixed it in. You already know that you've got 2.6 moles. And you already know that after it's mixed together with 2.6 moles, altogether you have 534 milliliters of the solution. What is its molarity? So molarity is going to be the number of moles divided by the number of liters. The number of moles in this case is 2.6 moles divided by the volume. How many liters is 534 milliliters? Okay, do you see that it is 0.534 liters? 534 milliliters could also be written as 0.534 liters of the solution. These are the same thing. You could have said, okay, I've got 534 milliliters times 1,000 milliliters is equal to 1 liter. So I take my milliliters, I divide it by 1,000, 1, 2, 3. That's it rewritten as liters. So 534 milliliters is equal to 0.534 liters. And we need our form to be in liters, moles per liters, as the standard. So 2.6 divided by 0.534, and it ends up through the math to be a 4.9 molarity. 4.9 molarity. That's shortcut for saying 9.4 moles per liter of sodium hydroxide in solution. There are 4.9 moles per liter. In the same way, the second part of the example asks the question, if a student dissolves 124.3 grams of HNO3, okay, in enough water to make 250 milliliters of solution, what is the resulting molarity? What's the resulting molarity? 124.3 grams in 250 milliliters comes out with a molarity of what? Now our formula would take us to say molarity equals the number of moles divided by the number of liters, right? That's our new formula. Okay, what are my number of moles? We don't know yet. We do know how many grams. So how do we go from grams to moles? Divided by the molar mass. So we'd have to go through and compute the molar mass of HNO3, take our mass, divide it by the molar mass. So another way of doing moles is equal to mass divided by the molar mass all over liters, right? That's another way of saying it. The moles, how many moles we have, is equal to the mass we have divided by the molar mass of the molecule we have. The molar mass they give us as 63 grams per mole. So we've got 124.3 divided by 63. So my mass is 124.3 grams divided by 63.0 grams per mole. That's going to be moles. My liters is going to be 0.250 liters. Okay, do you see that? Again, 250 milliliters can be written as 0.250 liters. So we have to keep our units right. Liters and moles. So our moles is 124.3 grams divided by 63 grams per mole. Our volume is 0.250 liters. And the math works out to be 7.88 molarity. It's technically 7.88.
So don't round it in this one?
Well, because in this one, if we look at significant figures, we've got this divided by this. The least sig figs in here are 3. So we need 3 significant figures. Right? Okay, apparently it's almost time to go, because books are going away and chatter's coming up. Hi. So we're going to see really quickly, we're going to do the dilution equation next, and then talk about using this in stoichiometry. Because you can see now, knowing our molarity, if we've got a 7.88 molarity here, let's say that we had a reaction equation, and we needed to figure out how many moles we needed in reaction, but we didn't have the number of moles, we just had its molarity. We would then need to figure out how much volume we needed of that 7.88 molarity to get the right number of moles so we can do the balanced stoichiometry. That's the next step. Of knowing your concentration and then driving that forward to give you a particular number of moles in your sample. So tomorrow we're going to do the dilution equation. That's on 332, and probably roll that right into using concentration, the next couple pages. We're going to finish with titration, because using molarity in stoichiometry leads us straight into titrations. And that's the end of this module. So there's basically 2 more days of instruction before we get into reviews and testing.